All right. Hello, everyone. So we have today one of our alumni from our guild, Shrenik, here. He's going to be talking to us about Koopman operator, introduction to a Koopman operator. He's also looking for collaborative work where we can have any of the students who are interested in working in this area. We can have a joint collaboration with him. So he's very much interested in taking this forward. Some of it he started off when he was just about leaving from here to pursue his PhD at Purdue University. So feel free to ask him as many questions as you can to find out more about what this topic is all about. And then we'll try to engage in some discussion after the talk. All right. Shrenik, all yours.
Yeah. So is my screen visible?
Yes, we can see it.
Hello, am I audible?
Yeah, can you go full screen maybe?
Sorry?
Can you go full screen maybe?
Yeah, sure. I guess this is the full screen only.
Oh, that is the full screen. Okay. All right.
Okay. Hello everyone. In today's presentation, I shall give a brief introduction to Koopman operator, along with some of the methods for finite approximation of Koopman operator, and followed by its potential application to ocean engineering problems. So it goes without saying that prediction of dynamical system is an area of research and industry. So the best way to think about a substitute model would be to use a cheap and fairly accurate approximation of the physics. However, for most problems of interest, the underlying dynamics tend to be extremely complex, which makes modeling a challenge. Traditional approach would be to make approximations of true physics, such as the use of a closure model. Yet this can introduce prediction error and uncertainty. So basically raise the question that is there some method to kind of project a dynamical system into space that simplifies the dynamics without physical approximations? So Koopman operator theory allows for precisely this, which is a method to simplify the dynamics that can be theoretically applied to all the physical phenomena. In recent years, Koopman subspaces has got a growing interest in academia due to theoretical promises. So in this presentation, I'll kind of discuss the foundations of the Koopman operator, followed by some of the methods by which, or some of the methods to make the finite approximation of these models, and shall finally suggest how these methods can be applied to ocean engine problems. The basic idea of Koopman operator is to lift the nonlinear dynamics into a higher dimensional space where its evolution is approximately linear. It's a linear operator that governs the evolution of scalar functions, which are often referred to as observables, along the trajectories of a given particular nonlinear dynamical system. So once good observables have been calculated, the nonlinear dynamics can be modeled as a linear model, which can be used for, say, predicting the trajectory of a nonlinear system. So these predictors can then be used to design linear controllers for the nonlinear dynamics. Now consider an uncontrolled continuous time nonlinear system as shown in the first equation, where X is an element of that state space S, and F is a vector field that lies in the same space as S. So in the discrete sense, it can be written as per the second equation. So instead of looking at these complex higher dimensional nonlinear systems, we actually take an operator theoretical point of view. So this is where the Koopman operator theory comes in. So instead of looking at how the nonlinear systems evolve, we actually look at how linear operator K, which is called the Koopman operator, when applied to scalar valued function psi, where psi is defined as measuring something of the states. We can actually compose that with our nonlinear update. And what we actually get is a Koopman operator acting on an observable psi, which is evolving in time. So we actually get dynamics on data versus dynamics on the states. And what's interesting about this formulation is that if you take something that is finite dimensional with nonlinear dynamics, you now get an infinite dimension operator K, the Koopman operator, but now it's linear. In other words, we can view the use of Koopman operator as a trade-off from say, simple observables and complex dynamics to complex observables and simple dynamics. So now what does it look like in terms of an example? So say you take a nonlinear dynamical system, which is shown in the slide. We can actually linearize this system depending on the types of measurements that we choose or scalar functions. So the measurement is just going to be identity, which is x1 as y1 and x2 as y2, and we are going to add a scalar value observable function, which is x1 square, giving us y3. Now, if we rewrite our nonlinear dynamics according to measurements, we can actually linearize the system, right? So now, if you think about this a little bit, what happened here is that we found a scale function, observable function, that when we apply an operator k, we actually stay within that subspace. So we found this Koopman invariant subspace where each observable function phi can be written as a linear combination of the other measurement functions. So unlike linearization techniques, which are able to approximate the nonlinear dynamics over a local region, the Koopman operator allows us to fully capture the governing nonlinear dynamics over the entire state space. So this linear system can then be exploited to design a linear controller for the non-dynamical system, a LQO controller. So does this procedure work for all examples? So, well, no. And there is a little bit of trick here. So say if we have a system shown on the bottom of the slide, in this case, the dynamics cannot be linear with just the measurement functions as x and x square. Because when we take the derivative of y2, we actually get an x cube. So as we try to build our Koopman linearized system, we do not get a closed invariant space, and we have to keep adding scalar functions to the set of equations. So now with the understanding of what Koopman operator is, the objective is now to formulate a method of learning these Koopman observables as well as the Koopman operator itself. So common methods include dynamic mode decomposition as well as scalar variants like, say, the extended dynamic mode decomposition and sparse identification of nonlinear dynamics. So in a general sense, what the DMD does is it tries to fit a best linear reduced order model, which can then be used for prediction and control purposes.
Shrenik, I
Yes.
think, can you slow down a bit? Sometimes we are losing your voice, looks like.
Okay, sure. So from where shall I start it again? Maybe
Maybe
the
from
point.
here you can begin, but I think sometimes we are losing your voice. Maybe what we can do is, if you want to try that out, shut off your video. Maybe that will improve the bandwidth a little bit,
Yep, sure.
and then we can continue. Yeah, I think you can start from here. I think would be a good way.
So yeah, shall I start from this slide then?
Yeah, yeah. And I would encourage all the participants, if you have any questions, please do feel free to stop him and ask him. Okay. So you don't have to wait till the end to ask him. Feel free to interrupt him and ask any questions you might have.
Okay, so now what does it look like in terms of an example if you want to see how Koopman operator works? So say you take a nonlinear dynamical system, we can actually linearize the system depending on the types of measurement that we choose or the scalar functions. So the measurement here is just going to be identity, which is x1 as y1, x2 as y2, and we are going to add a scalar value observable function, which is x1 square, giving us y3. So if we assume these three as the states of the system, then we can rewrite our nonlinear dynamics according to these measurements, which can actually linearize the system. Now, if you think about this a little bit of what happened here is that we found a scalar function observable, or say observable function, that when applied on some Koopman operator k, actually stay within that subspace. So we found this Koopman invariant subspace where each observable function psi can be written as a linear combination of the other measurement functions. So unlike linearization techniques which are able to approximate the nonlinear dynamics over a local region, the Koopman operator will allow us to fully capture the governing nonlinear dynamics over the entire state space. So this linear system can then be exploited to design a linear controller for the nonlinear dynamical system, say a LQR controller. So now the question arises is does this procedure work for all the examples? Well, no, it doesn't, and there is a little bit of trick here. So say if we have a system as shown in the bottom of the slide, in this case, the dynamics cannot be made linear with just the measurement functions as x and x square. Because when we take the derivative of y2, we actually get an x cube, right? So as we try to build our Koopman linearized system, we do not get a closed invariant subspace. And we have to keep adding scalar observable function to the set of equations. And the matrix would keep on multiplying.
Oh, so you mean to say that the size keeps increasing. There is no a finite set of inputs which I can choose in which I can finitely represent the dynamics.
Yes, right.
All right.
So now with an understanding of what Koopman operator is, the objective is now to formulate a method for learning these Koopman observables as well as the Koopman operator itself. So common methods include dynamic mode decomposition as well as its similar variants like the extended dynamic mode decomposition and sparse identification of nonlinear dynamics. So in a general sense, what the DMD does is it actually tries to fit a best fit linear reduced order model, which can then be used for prediction and control purposes. So before diving into extended dynamic mode decomposition, I'll try to first explain what dynamic mode decomposition is. So just say we have a lot of data with us. So DMD is an emerging purely data-driven technique to obtain, say, linear reduced order models for a higher dimensional complex system. And in addition to reduced order models, we can also extract from this data the patterns that dominate measured observable data from that dynamical system. So this was initially introduced in the fluid dynamics community in the year 2009, I guess, by Peter Schmidt. So what the DMD first does is it takes all of the data in time, and what it does is it organizes the data in big matrices, say X and X prime. So the columns of X are the snapshots of the data, which is reshaped into very, very tall column vectors that are evolving in time. So each column of that matrix represents the extended state at that time.
So
And
this means if I chose x1 would represent the fluid velocities, let's say, over the entire domain mapped into a single vector.
yes, right.
So if I had
So
a huge grid, so it will be as tall as the number of grids I had in my domain.
yes.
All right.
So the columns of X are basically the snapshot of the data. So each column of the matrix represents the extended states at that time instant, and X prime is the exact data matrix X, but advanced by one time step into the future. And then what the DMD does is it tries to find a best fit linear operator A that advances X into X prime. So the basic assumption is you can write down these dynamical system in terms of a linear dynamical system, which is X prime equal to A times X. But the problem is, since we will be dealing with millions and millions of measured data, this A matrix will be a million by million matrix, right? So we definitely would not like to compute that A matrix. So what the DMD actually does is it approximates the leading eigen decomposition of A matrix without actually calculating the A matrix. So the figure shown here is a kind of a cute representation of what DMD is. So the singular value decomposition that we do uh, in a dimensionally reduction step is the principal component analysis. So over here, what the principal component analysis does is it takes this dimensional data and kind of finds it for the fewest dominant patterns that explain the data. So in principal component analysis, we kind of find that matrix A, whereas what Fourier transform does is it diagonalizes that linear model to find the dominant patterns in time. So otherwise we can say that DMD is just a combination of these two, which is PCA and Fourier transform in time. So now talking about what extended dynamic mode decomposition is. So it is a mode decomposition algorithm, which is a popular numerical method for obtaining finite sections of the Koopman operator that has proven useful for predictions and control in nonlinear system. So extended DMD is modification of exact DMD that strengthens the connection between DMD and the Koopman operator. As the name implies, extended DMD is an extension of DMD that uses a richer set of observable functions to produce more accurate approximations of the Koopman operator. It is also demonstrated that the DMD and related methods produce approximations of the Koopman eigenfunction in addition to more commonly used eigenvalues and say modes. In other words, it is a method for generating an approximate. So it's a method that is used for generating a linear differential equation in a chosen basis of observables, which can be actually decided by the user. So if X and Y are the data matrices containing points of the same trajectory and psi is a basis, then EDMD approximates the Koopman operator as per the first equation, where the cross sign represents the pseudo-inverse of a particular matrix. So in the discrete sense, the model can be stated as per the last two equations.
So what is X and Y in this case?
X is this. So if you look over here, X is the snapshots of the data with time. And Y is just the data shifted by one time instant. So there's an issue of nomenclature here. But
Okay.
Y is not the output here, but
Y
Y
is
is
known as
the,
X prime in your previous picture.
yes, right.
Okay.
So now I will try to explain how the EDMD method could be used to compute the A, B, and C matrix linear reduced order mode. So here X matrix is the data for different time instants, whereas Y here is the same X matrix, which is shifted by one time step into the future. And U here is the matrix containing the input time sequences. In other words, we can say that it satisfies the relation of Y is equal to f of X comma U. So provided we have this data, X, Y, and U, A and B are obtained as the best linear one-step predictor in lifted space, in the lifted Hilbert space, in a least square sense, which can be seen in equation 2. So here Y lift and X lift are the lifted states of X and Y. So these lifted states are calculated by combining the actual states of the system with the nonlinear functions of the actual state. So these nonlinear functions of the actual state could be anything like, say, the radial basis function, monomials, and so on. Similarly, C can be computed by minimizing the third equation. So the analytical solution to this equation is shown below, where A and B here is just Y lift multiplied by pseudo inverse of X lift, comma U. And C is just X times pseudo inverse of X lift. In an ideal case, it would be such that X would represent the actual states of that system.
Shrenik, can you pause for a minute here? So you're taking
Yeah.
a in pseudo inverse of X lift comma U.
Yes, right.
So, okay. That is
Yeah,
interesting.
so I'll try to explain how it comes like that. So just say Y lift is just the X lift, but shifted by one time instant, right?
Correct.
So we could probably write Y lift as A times X lift plus B times U, right?
Correct.
So we can calculate AB by just multiplying Y lift by pseudo inverse of X lift by U. This
No,
would
no,
be it.
one second here. My confusion is this in the sense that what is the size of this U?
So the U size is the like if we say if we have a k number of time steps
Hmm.
and each state represent is of dimension 2, then the dimension of U is the dimension of the lifted state cross the number of time steps.
No, no, let's say that I was talking about your fluid mechanics example from previously. So let's say I had a million grid points. So which would mean that x1, x2 to xk are all million cross 1,
Yes, right.
right? And y1, y2 and y3, they are all also million cross 1,
Yes, right.
right? Now what would be u in this case?
Yeah. So U would not be extended in this case. It would just be the dimension of the actual inputs that are there in a linear dynamical system. Just say for the million dimensional state space model, if we have the dimension of control input, we say only 3, then that would be it won't be extended, and that's the actual benefit of Koopman operator we get. That
So
only lifts the
it would
states of the
be,
system and not the input.
so the matrix capital U would be 3 cross the number of
Cross
time
number of
steps
yes, right.
that I'm considering. So 3 cross k.
Yes,
If there were 3 control inputs,
yes, right.
right? So here we're talking, if we are talking in terms of a fluid mechanics problem, we would probably be referring to 3 points where we can actually control something in the fluid flow.
You could say that.
Now, sorry?
Yeah, yes, you're right.
Okay, and then this lifted dimension will be a higher value. So it would have not only just these. So would the lifted dimension always have the original independent states as a part of the lifted dimension, or can they be always be different, altogether be different? So for example, if I had x1 and x2 as the original state, does x1 and x2 also have to be part of the lifted state, or can the lifted state simply be x1 square, x2 square, x3, x1 cube, x2 cube, something like that?
Yeah, it has to be the part of the lifted state. So X lift or Y lift, whatever has been stated in the presentation, would be just the concatenation of the actual states followed by like a nonlinear function of these states.
Correct. So the
These two
original exists.
concatenated together.
So the
So
original
the
exists, and we add some more states to it.
yes.
Okay, all right, got it. Now, when you say you lift, how do you lift you up?
No, I guess that's wrong nomenclature. I guess it should be just you.
It should
Is
have
it
been just B
ending?
times U.
Yes. So I guess so.
Okay, all right.
So now main drawbacks of traditional DMT-based methods is that one needs to pre-specify a library of potential observables, right, to learn
Shrenik,
the
can you
Koopman
go
operator.
back one slide if you wouldn't mind?
Yeah.
Okay, so here you are saying that the analytical solution part is still confusing for me. How are you
Okay.
getting the, so your X lift is a million cross K, or maybe it is not even million, it might be 2 million cross K, let's say, because it is in a lifted dimension,
Yes. Correct.
right? And your U is say 3 cross K, then you
Yes.
can't directly concatenate them,
No,
right?
I mean concatenate along the columns, or just say concatenate just below that. Then it can be done, right?
Oh, so you're putting it in concatenation along the row dimensions.
Yes. Right.
So it will be 2 million plus 3 cross K.
Yes.
All right, and then you're taking the inverse of that, and that would give me A and B concatenated. That's what is the point.
Yes. Right. And the reason why we can do that is because the data would be fixed. Because once we have calculated X lift and Y lift,
Hmm.
this can be done, right? We are not actually like using a neural network to minimize X lift or Y lift or something like that. If that was the case, then we could have not used this. Over here, X lift and Y lift is fixed once we have the data with us.
Correct. We
Once we
exactly
have that
know.
data, yeah, we exactly know that. So from that, we could directly calculate A and B.
Okay, all right. And C basically is basically trying to transform you back from the lifted dimension to the original dimension. So C times
Yes.
itself will give me Cx. That's what is the idea. Okay.
Yes, and like you actually also don't need to calculate C if you know like where exactly are you putting the states in that lifted states. So in an ideal case, C would be such that X represents the actual states of the system. So if we say take the first two states as the actual states followed by nonlinear functions of state, the C would be just 1 0 0, then 0 1 0 0, and the remaining ones would be 0.
Correct. You'll be simply be extracting certain states from the lifted dimension, and that forms your actual state actually.
Yes, actual state. So if you kind of do the regression analysis also, you would find that C would be close to the C that I told you right now.
Okay. So
So
now typically you want to compute A and B. You don't want to compute A and B.
no, I want to compute A and B because if I am able to find out A and B, then I can write it in the linear fashion as x dot is equal to A x plus BU,
But
where
it
x is the
is
lifted.
quite a computational challenge, right? That's what you were talking about previously, wasn't it?
Yes, the computational challenge is with regards to Koopman operator, but DMD is not that way. So what DMD does over here is it actually only takes the measured data that it has with it, and then it does a regression analysis.
No,
But
no,
what
the
X, yeah,
extended one, we are doing the lift, right?
yes, we are doing the lift, but over here in this case we are kind of defining how much lift we are to take, like how much nonlinear measurements of state that we ought to take, so that the model that we get is almost close to the Koopman operator. So what Koopman operator does is it's basically an infinite dimensional operator. So it says that if you extend it to an infinite dimensional space, its evolution is linear with time. But practically speaking, it's not possible in that way. So what extended dynamic mode decomposition tells us that it gives us a finite approximation of the Koopman operator and says that if you take the actual states of the system, followed by followed by some of the nonlinear measurements of that states, then you could probably generate a linear model such that it's close to the approximation of the Koopman operator.
So,
So
but we
what
don't.
happens is,
So the problem is to find what should be these augmented states.
yes, correct. So the augmented state can actually be a non-linear function of the first two states. So it can be, say, radial basis functions, or say you could keep it as monomials, depending on what dynamic is. So just if you have x1 and x2 the states of a nonlinear system, you keep the third state as x1 square x2, then the fourth state as x1 x2 square, and the fifth state as 1 cube x2, something like that. Monomials.
No,
Or
but
one of the other
is
methods,
this decided by the user or is it decided by
it's
the?
decided by the user. So till now there has not a decent research on how exactly, or is there a systematic way to find these observable functions or extended states as such.
So
It's
there is
just some
no.
trial and error as you try this approach, try this observables, and you see whether you can
Okay, okay. So it is a
get a good
trial and
result.
error basis on which we try to find these augmented states such that this method can work well.
Yes, right.
Okay.
So the uh,
Yeah, yeah. Go ahead.
yeah. So now the main drawback of traditional DMD-based method is that one needs to actually pre-specify a library of potential observables to learn the Koopman operator from. But since true Koopman observables are not known, we could probably use a deep neural network to calculate the ideal set of observables. So in the deep learning approaches, a neural network is used to provide a learnable function from the system state variable to the Koopman observables, and say vice versa. A DMD-based algorithm can still be used to find approximate Koopman operator, yet there is no need to provide a library of observations since the neural network will learn them. A neural network is attractive since it allows for the Koopman observables to potentially be extremely complex with respect to the system states if needed. Additionally, such deep learning methods are easy and they tend to be simply fully connected models. Now, no prior expertise is needed to try to guess good observables. Instead, you let the deep neural network and gradient descent figure it out for you. So this neural network mainly consists of two networks. one to encode the input states to the Koopman observables, which is the extended lifted state, and the other to decode Koopman observables to state space, the actual state space. So the loss of the model mainly consists of four components, which is the reconstruction error, the state prediction error, the Koopman operator error, and the Koopman operator decay error. So now talking about this application to ocean engine problems, these methods could probably be tried out on vessel dynamics shown in the slide, because the first equation could be solved to obtain the, say, the surge, the sway, and the yaw velocity. So here F2 and F3 are the expression which consists of linear terms with higher order hydrodynamic derivatives, where F1 consists of the propeller thrust T in addition to this higher order hydrodynamic derivatives. So if anyone is interested, they can try implementing these methods and see whether they are able to model the ship's dynamics accurately in a linear fashion. Yeah, so that's all I have.
Okay, fantastic. Any questions from our audience? I'm sure there must be. Now is the time to ask him to go back and talk about the parts which you probably did have difficulty in understanding or you were not clear about. He'll be able to probably throw some more deeper light at it. And I'll come back to my questions at the end. Please go ahead.
Like I had that a bit difficulty in understanding that part related to you, like the
Okay, where exactly?
X, yeah, this, yeah.
Okay,
You
so
were discussing with like about the dimensions and all, so that part, like,
okay, so you wanted to know like what should be the dimension of the
the voice is a little breaking.
Yeah, am I audible?
Yeah, let me shut off my video so that it helps a little bit. Yeah, I think you're audible. Yeah.
Yeah. So over here, what we're kind of doing is just say you have this dynamics with you. Okay. Let's talk about this dynamics. Okay. So if you see here the number of states in that non-linear dynamics is just two, which is x1 and x2. Okay. So what we're doing over here is, if we are in this case actually able to write this dynamic in a linear fashion as y1, y2, and y3, right? Which has a 3-dimension. So over here, what we are kind of doing is we are taking the dimension of x lift to be 3, dimension of y lift to be of course 3 cross k, and x lift dimension to be 3 cross k, where k is the number of time steps. So just say if you do evaluate for just around 100 seconds, the k would be 100. If the time is 1 second. So you have an x lift matrix which is a 3 cross k 100 matrix, and y also which is a 3 matrix. But the difference between y and x lift here is y lift is just x lift shifted by one instant. So whatever x lift you have 0 to 100 seconds, y lift would be just that but shifted by one time instant. So what we are kind of doing here is we are trying to do a regression analysis which we kind of find a and b by just multiplying y lift into pseudo inverse x lift component. And the u here won't be extended. So see over here, the dynamics that we get is x1, x2, right? Which is a two-dimensional vector in the non-linear sense. If you look at the Koopman linear sense, we have a dimension of 3. But the dimension of u won't be 3. It would remain same as what was the dimension for the non-linear case. And that's the reason why u won't be extended. And just in this case, it was just 2 cross 1. So it was just 1 because saturation is only affecting the second state. And in turn is affecting the first state. So u will be just 1 cross 100 in this case.
So like can I say that the u is something like we can't like give additional controls to, like we can't create additional controls, like they will be whatever they were before only.
Yes, right. And that's the added benefit of Koopman operator, because if we are able to do that, we don't need to there won't be multiple degrees of freedom to control, and there would be just things to control which are actually there in actual nonlinear system, right?
Hmm.
So it doesn't mean that these inputs that we provide to the model when it's linear, model, it doesn't mean that it won't affect the remaining state which we have as something. It will affect the system based on what A matrix we get. So it's simply similar to saying that in what happens in Koopman operators, we are kind of lifting it to an infinite dimensional, and if we do it for an infinite dimensional space, we can of course make it to be, we can make the linear model to be exactly represent it as a non-linear model. But over here, in practical sense, it's not possible because we can't dimension to an infinite space, right? So what EDMD does, it tells you that you choose a basis of observables that you want, and based on that you extend the states and see whether when you have extended the state and you're propagating time, it should happen in a linear way. And if the trajectory that you get, the state's evolution with time that you get, matching with the state's trajectory for a nonlinear system, then you can say that your linear reduced order model is a good approximation of the nonlinear dynamics, right?
Hmm.
And say the trajectory of that state in linear case should match the trajectory of the nonlinear system for a reasonable duration. Say if it's for 200 seconds, then you can almost say that your linear model is performing similar to the nonlinear model. And if we are able to do that, then the benefit that we get is we could design linear controllers, say PID, PD, whatever controllers that we have on a linear dynamical system.
So Shrenik, if you come to your last slide,
Okay, this one.
no, yeah, this one, yes. Would I be right in suggesting that the extended modes be V cube, R cube, VR square, RV square, delta cube, and so on and so forth?
Yes. So in this case, if you look at the dynamics, it feels that the non-linearity is mostly in the form of polynomials, like say V cube, R cube, square. So if you're able to extend that states from just if the actual states are U, V, R, and X, Y, Z, is say are the actual states. When we write it in states form, we could probably extend the states as V cube or R cube, V R squared, and V squared. And by doing that, what we are doing is we can write it in a linear fashion, but that won't be true in this case. We have to write a lot of other monomials, because to take R cube as the state system, then the derivative of that would be 3R squared times R cube, which is R to the power 5. Then you have to take R to the power 5 as one of the extended states. So that will continue to be infinite till to be infinite till time.
So it may not close out, right?
Yeah, it may not close out, but if we are able to do that for a particular time, say for a particular duration. So if you're able to till say R power 5 only, and after that you don't extend, just keep it till that. Although like derivative R power 5 is not there.
So
But by doing that, if you're able to get the trajectory, like if you're able to get decent predictions, then you could stay with that, right? And say that by just extending till this point, I'm getting decent prediction.
no, but then my dynamics is incomplete. What do I do for the R to the power 5's derivative? I set that as 0.
Yeah. So what happens is as you keep on increasing terms as you keep on increasing states in a rifted state, what happens is you're approaching close to the actual nonlinear system. So over here, what we are doing over here is that it's the similar thing that we are doing here. So over here, as you keep on increasing the polynomials, say if you only stop till y power 4, you might get prediction which is closer to nonlinear trajectory, but it won't be exact. But as you keep on extending it from y to the power 4 to 10, you might be going close to actual nonlinear system.
No, but then the problem still remains, right? For example, if I only considered states till y4 in this particular case, let us say, okay, I may be looking as my solution might be looking closer to the original nonlinear system solution, maybe say up to 100 seconds is where I have the data. But if I extend that further and start looking at 200 seconds, there's no guarantee that this thing will converge when I only take Y4, right?
Yes, will converge, but it won't be exactly tracking what it is. So over here, just say if you go on stop only till Y4, you might not get a good accuracy. So just say if you want to try a sinusoidal wave and you keep Y4, you only truncate it till Y4,
So
you
sorry,
might not get a good tracking, and you might have an amplitude smaller than the sinusoidal waves amplitude.
sorry, I lost you there. Could you repeat it again once more for me?
Yeah, sure. So just say if you want to track a sinusoidal wave, so if you see the trajectory of the nonlinear system to be sinusoidal wave, and if you only truncate it 5 to the power 4, it will track the sinusoidal wave. But it won't have the same amplitude as it had for the actual nonlinear systems. So if you kind of extend that it from Y4 to say Y500, you might see that it starts to converge to that trajectory and you see the good performance. So it's actually a trade-off between how much performance you want and how much computation you want. So if you say that like you have a computational resource of only extending the states up till 500, then you have to stop at that point, because if you extend the states from 500 to say 600, your computation would be more, which is what you don't want. So for 500, whatever performance you have, if you're satisfied with that, then you should go with it. So,
So would I be right that when I want to do this, I want to kind of trade off between designing a linear controller for a high dimensional system, how much computation overhead am I getting, versus designing a nonlinear control for a nonlinear system?
yes, and also there is something that it doesn't always happen that as you keep on extending the states, you would keep on getting good performance, like better and better performance. So what happens is after some point it tries to saturate. So it's a curve like a time constant, you can say. Like if you can, it actually the performance keeps on increasing if you extend the states for say 100 to 100. But after 500, if you take 500 number of states, you take 1000 number of states, doesn't matter, because at that point the performance has saturated, and even if you take a higher dimensional states, it's not going to matter much. So we could probably stop at 5. So we have to find a kind of figure out as to till how much state should we take the monomials into account, such that after that, after adding a higher number of monomials after 500, we can, there's no like need of doing that.
But does that not depend on how much time step data you have?
Yeah, it also depends on that. So it actually depends on the data that you give, first of all. So you need to give a lot of data for it to understand all the behaviors of the system. So the data has to be low. The other thing is you should choose the right set of observables. Those observables, I feel, for this dynamics of ship is be monomials only, because you have monomials as your non-linearity in the dynamics. So you have to assume monomials of different powers such that sum of the power is constant. Just say you assume a monomial of form u to the power a, v to the power b, c to the power d, and sorry, u to the power a into v to the power a, d into r to the power c, such that a plus b is 1. Take all the combinations of that and generate monomials and see how it performs. Then you again extend such that a plus b plus c is 2. So then you have more monomials to it, and then see how it performs. And you add more monomials and see how it performs. So by doing that, we have to observe whether we are getting a finite approximations of the Koopman operator.
Okay, all right. I think I fairly understand it now. But how does
And the
it tie back to the Koopman thing where you had an infinite dimensional thing?
yeah, so Koopman operator is just an operator which is that if you extend the states to a infinite dimension, it would be linear, of course, and that linear model would exactly represent the nonlinear system that we have. But what EDMD tells is that just say if you choose a right set or say a right basis of observables, you can only stop till a particular point, because after that point, you're not going to get an improvement in performance. So it's going to saturate up till that point. So there is no point taking the number of liquid states higher than 500. If at 500 only, the performance is saturating.
Okay, got it.
That's
I'm going to leave it back to the others to ask questions before I come back.
Hello.
Yeah.
Yeah. So correct me if I'm wrong. What I understood by Koopman operator is, let's say we have a two-dimensional nonlinear system, and traditionally what we do is we linearize the system, nonlinear system, about some equilibrium point, right? Then we can analyze that system only nearby that equilibrium point. If you go farther away from that equilibrium point,
It won't.
our approximations will get wrong, right?
Yes.
So this Koopman operator is doing something that it takes this two-dimensional system to some, let's say, higher dimensional, 10-dimensional, let's say, and there it is linear over the whole state space.
Yes, right.
And all the linear control methods, let's say PID or MPC, something like that.
Yeah, could be applied to the nonlinear model because you got a
So,
fairly decent approximation of the nonlinear dynamics.
so that's what in this slide I didn't understand. How are we going from, like, this is a two-dimensional system, right? X and X square.
Yes.
So how are we going to that higher dimensional space?
So in this example, if you observe that if you take higher order terms like x cube, x power 4, in order for the model to be linear, you have to keep that as infinite, right? So if you take x cube, its derivative would be x power 4. Then you have to take x power 4 also as observable, or also as state for it to be linear. Then if you take x power 4, then you have to take x power 5 also as state.
Yeah,
Then it goes
this
on.
thing I didn't understand. Like to make it linear, we have to take higher order, like x power 5, x power 6, and so on. I didn't understand that.
Okay, so I'll try to first explain this part, and then I can explain you the other part.
Okay.
So for this dynamics, if you look at the nonlinear dynamics, you have the states as x1 and x2, right?
Yes.
And you have a nonlinear term of x1 square over here.
Yes.
So just say you assume x1 square as the third state. Then can you write the nonlinear dynamics in a linear fashion? Yes, you can write, right?
Okay.
Because the derivative of x1 square is what? It's 2x1 times x1 dot, right?
Yes. Okay.
And x1 dot is what? It's x1. Or you can say mu x1.
Okay.
So it's x1 square again. So it can be written as the third state itself. That's why we can say that the third row is 0, 0, mu. So for this example, you can actually stop at one point and say that if I assume states, then my model is linear. And this would be this Koopman.
Shouldn't mu be in the beginning of that row?
I don't think so, because y1 is x1, y2 is x2, and y3 is x1 square.
So if I take a derivative of x1 square, I get 2x1 times x1 dot, right?
Yeah.
Which would be x1 dot is mu times x1.
Yes.
Right, so it should be multiplied by y1, right? Which means that's what it should be.
No, like the y3 is x1 square, right? So you should look at the third row.
Correct. So the third row, the derivative of y3 should be
Yes.
2 times x1 times x.
Yeah. So see, if you assume y3 is as x1 square, so the derivative is 2x1 times x1 dot, and x1 dot is x1. So it is 2 times x1 times x1, which is 2 times x1 square. And of course, there is a multiplication of u as well. And x1 square is assumed as y3. So it's 2 mu y3.
x1 square is assumed as y3.
Yeah. And the derivative of y3 is 2 times x1 dot.
Correct.
And x1 dot is x1.
2 mu times x1 square. So that is why 2
Yes.
times y3. Okay, got it.
Yes. So in this way, we are kind of stopping till one point. So over here, Koopman linear that we get and the non-linear is will be exactly matching.
So this y system, this will be linear. That is what you are telling, and that
Yes.
will be linear for the whole state space.
Yes, for the whole.
And
state
here we can apply our linear laws, linear control laws, right?
Yes, right. Yes.
Okay.
And what is happening over here is, just say if you take for this dynamics of x dot is equal to x square, if you assume the states as and x square only, you can't write it in a linear fashion like this. Because just say if you take the state as x square, what would be its derivative? Its derivative would be 2 times x dot. And what is x dot? X dot is x square. So it would be 2 times x cube. But we don't have a state which has the term x cube in it. So we have to assume another state as x cube. And if we do that, we would have a term called x to the power 4. And
So
we
like
won't have
this, you
x
will
to the
go to
power.
infinity.
Yeah, and like that, we would be go to infinity. So what happens is, as you keep on increasing the states, higher order terms, the performance will keep on saturating up to a particular point. And after that point, there is not much improvement in performance. It will improve. It will keep on improving until it until it's equal to the nonlinear system.
Performance in the sense like approximation means.
Yeah, approximation.
Okay.
So it's not able to approximate the nonlinear dynamics that better. So it depends on how much, till what point you want to stop. So
Shrenik, I have a question. Can you go back to your previous slide? So suppose I want to truncate at y4.
yeah.
Okay, what will that matrix which will be there? What will the truncated matrix look like? Won't it have all zeros in the one row? Would it not become what you call the rank would not be a full rank, right?
Yeah, but then we won't be able to write it in a linear fashion only, right? If we just truncate it till y4, it's not linear. So how can we write it as ax plus bu?
But then when you say I'm going to truncate it at some point and see whether it has saturated or not, when you do the truncation, how do you truncate it?
No, we actually don't do the truncation. We actually stop at that particular point. So at that point, it's not linear. It's just that if you kind of take that system into account, and when you integrate it and see the trajectory of the system, it will keep on getting closer and closer to the linear model.
So the output of a EDMD is not a linear system.
No. So it's
But
not.
then how do we go ahead and apply the linear control laws?
No, like you didn't understand. So in this case, there is no option but to extend the dimension to a infinite space. You can't stop at one particular point, x4 or y4 or y5. But just say if you have a dynamics like this, or say you have a dynamics like a ship.
Correct. So suppose I have a dynamics like a ship. Let's see. This
Yeah.
also won't stop. No, that is my point. This also will go to infinity.
Yes, I understand. So what I'll explain from this point again. So just if you stop at y4 only, you would have a term called x to the power 5 in your equation, right?
Correct.
But x to the power 5 is not the state of your system, so you can't represent it in a linear fashion. But
Correct.
what happens is, as you keep on extending the dimension, that x to the power 5 is of not much importance to the model. So just say it's like it's similar to Taylor series expansion, where you take the higher order terms in it, right? So you write f of x plus f dash of x by 2 factorial plus f double dash by 2 factorial, 3 factorial, and then you keep on adding. But you say that for a good linear approximation, you truncate all the higher order derivatives. So it's similar to like that in that way.
No, but I
So
need a linear system at the end of the day, right, to formulate a control law, don't I?
yes, correct.
So what will that linear system look like?
Yeah, so the linear system will actually look like based on these equations. So just say you have, talking about this dynamics only, okay? How we can generate a linear system is, I can tell you now. So just you have the states, actual states as x, y, z, u, v, and r. That's your actual states. Okay.
Okay.
And you assume the other states to be these states followed by, say, all the terms that you have in the as non-linearity in f2, f3, and f1. Okay. And you extend that. So now just say you simulate the trajectory or you generate synthetic data for this non-linear dynamics of the ship that you have, which is given by the first three equations. Okay, we can do that. We can generate synthetic data for that.
Correct.
So we have the trajectory of u, v, r, x, y, z of the state of the system. So once we have that, we can calculate v cube, r square, v square, delta cube, whatever are the remaining states, right, from that, because we have the data for u, v, r.
Okay.
Okay, so we have all this data which is extended in space or till a particular point that we want. So we have this data, so we have already computed x lift and y lift, and we also know the u.
Okay.
So from that we can calculate AB just using AB is equal to y pseudo inverse of x lift comma u. So once we get A, you need to provide the initial condition of the ship at the first time instant. So that is one of the drawbacks of the Koopman operator. So for the Koopman operator, you have to assume that your state of the ship is known or it's observable, since that at t is equal to 0, you know where the ship is exactly and what is its speed and say the location.
No,
Once
no.
you know that,
My point is that that A matrix which you formulated now,
yeah,
right? How are you ensuring that it has a full rank? For example, the example that you showed, clearly there we cannot have a full rank. One row will become zeros, right?
no, it won't become zeros.
No, the example that we had
Okay,
previously.
you mean this one, right?
Yes, this one. One row is becoming zeros, right? If I truncate at x4, I see all zeros. Or if
Yes,
I truncate at y3, I'll see the last row is always zeros.
yes, but when you're truncating at a particular point, you're not assuming the model as linear. So this case is totally different from this equation EDMD. So this is not EDMD basically. This is not EDMD. So just we're telling that if you want to make the model which is linear to be exactly matching the non-linear model, you have to make it infinite dimensional. And this is the explanation for Koopman operator.
So if I wanted to apply, say, DMD to this system, how would I go about doing it?
Yeah, so EDMD, so for EDMD, you have to basically choose the set of observables that you want. Now you can't choose the observables as h square, x cube, x to the power 4, x to the power 5, and something like that. Because if you in case you do that as extended states, you cannot make the model linear, as you can see from this slide, right?
Correct.
If you
So my
truncate at a
point
particular
is
point,
that so I'll
you
end up
can,
with a singular matrix. So which means I can't find a solution for it, right?
yes, you can't find a solution for it.
So I have
So
to
if you want
epic
to
mod,
apply it, yeah.
have
So
to
if you
edit
want to
my
apply,
state.
okay. So
Sorry.
if you want to apply, yeah.
Okay. All right. Why
Okay.
don't you first talk and then I'll ask?
Okay. So if you kind of want to apply EDMD on this dynamics, we should not use x to the power 4, x to the power 5 as our extended stage. Because if we want to do that, then we have to extend it till an infinite dimension in order for us to calculate A and B. So if you want to apply EDMD over here, we could probably use other functions like say radial basis functions as remaining states. So if
But
you use that, then maybe you could get finite
how
approximation.
do I know that ahead of time by looking at the system? What should be the states I should choose? How do I decide on that without by just looking at the dynamics of the system that I have?
Yeah. So that is something we need to decide upon. The user needs to decide as to what, looking at the dynamics, how exactly should I find the observables. Now for this ship's dynamics also, I'm not telling that monomials are going to be working best. Because for monomials to work good, you have to extend it for till an infinite dimension, which is not possible. So you should not assume the observables as monomials also. You could probably have radial basis functions. So radial basis functions are like, say, you could take polyharmonic radial basis function and which is a nonlinear function of the states, and then you could probably extend that would be linear. That's the reason why during the time that I had tried applying this approach on the ship's vessel, initially I tried to use monomials only, but monomials won't work here because rank is not defined if you stop till a particular monomial.
Correct. You will say run into the same problem as the example that you showed.
Yes. So
So
that's
then
the issue
you
over here. So we
have
should not assume that as
yeah, you'll
monomials.
have to choose something else as the basis, which you are suggesting as a radial basis functions. If we choose, they have the representational capacity to capture the dynamics.
Yes, right.
Okay,
And
got
what
it.
happens is as you keep on increasing the end lift, it will stop at particular point. So from 100 onwards, it won't be too much. So you can just stop till 100 and say that this is my linear model and it's matching my nonlinear system's trajectory quite well. So I could design a controller based on that linear model and use it for and use it to apply it on a nonlinear shifts dynamics.
Okay, all right. More questions from others?
And currently there has been a lot of research on Koopman. Just the things that I presented is just basic Koopman. It's nothing. So there's a lot of research on Koopman, and generally like in recent years from 2016 there are almost 400 papers that get published on Koopman. So whatever I've told in this presentation is very general and basic.
That's fine. At least we are getting introduced to it.
Hello.
Yeah.
Could you once again explain that DMD, EDMD? Why is it even required for this? Means what was the context of talking about that? I didn't understand.
Yeah, so the
DMD.
context of why we require DMD or say EDMD is we just want to generate a model, a linear model, such that it can be computationally efficient. If we use a Koopman operator, we have to extend it in infinite dimension, like this example, which is not possible. So what EDMD tells is that you decide what basis functions that you want to choose, and you extend it till that point. It could be
Basis
Koopman.
basis basis function
No,
means the states. What does it means?
no, like basis means like you could tell how you could tell what should be the nonlinear function of x that you want for it to be extended. So it could be rated basis functions or say other types of basis functions.
I didn't understand actually.
Okay. So practically speaking, there is no like hard and fast science as what should be those functions be. So you could probably depend on that. So just say you have x1 and x2 as your system, actual states. Based on the dynamics, you have to decide what should be my remaining state such that the model is linear. So you could
So
probably
per
say x1 cube as my third state, x to the power 4 as my fifth state. And that is EDMD, which because you are defining the other functions. So
okay.
other functions are defined by you, and then you're linearizing the model.
Okay, so now in case of the ship dynamics, we have to decide this properly. What should be our basis functions,
Yes, right.
and then that will do efficiently. It will be able
Yes,
to solve, or it will be able to convert it to a linear system in higher
yes.
dimensional space. Okay.
So what data you take, like even if you take millions of data, if you don't have the right observables, you're not going to get good approximations of the nonlinear dynamics. So for the Koopman operator to work, you should know those observables. And these observables are something which we need to decide upon. And since we can't do that, that's why there's a concept called deep Koopman, which is a
Oh,
two types of network in which it maps the input to the extended states and then again decodes it to the actual states of the system. By that, what we're doing here is the neural network is learning the behavior as based on the data that you provide. It's learning what should be the observable, what the observable should be. And since neural networks are more complex, they can learn that behavior pretty well as compared to
So it is learning
user-defined.
what would be the lifted dimension.
Yes. So by learning the different dimension, it's indirectly learning the remaining states that we want to take into account, right? So
Okay,
that's the
and you
reason why
don't know whether they will be what you call monomials. They probably will not be monomials.
yeah. So there could be some nonlinear functions. So it depends on how the neural network is. So whatever the neural network gives us output, that would be that.
Yeah, it will be like suppose it has 4 layers, then it will be some complex sigmoid functions of some combinations of sigmoid functions of combinations of the input.
Yes. Right.
And
So
that would be the lifted state.
yes, that would be the ideal state because we don't know prior what should be the ideal state. So just say if I use radial basis function also, and I'm getting good performance, but what is a guarantee that I might not get a more better performance if I use different observables? So by using deep Koopman, we can solve that issue.
So it's an encode. No, it's not.
Yeah, it's an encoder decoder network. So first what it does
Correct.
is it encodes and then it decodes.
Okay, all right.
And one more, yeah. So now talking about the limitations of Koopman operator, there are basically a lot of limitations. So first is that even after you linearize the model, okay, you did that, you have to assume that you you have to assume that all the states that you have are fully observable, right? Then only you will be able to propagate from say k to k plus 1, or say from k plus 1 to k plus 2. So that is one of the limitations which you need to have.
Sorry, they should be fully what?
All the extended states should be fully observable for the model to work, which
They
should
should be
not.
fully observable. Okay.
So that is one of the case. If that's not the case, then we can't apply Koopman. And the second case is that it's quite sensitive to measurement noise. So even if you add a slight amount of measurement noise to the linear model, it's going to work very bad. So it's quite sensitive to measurement. Third case is that it cannot handle uncertainty that good. So these are the four main.
I can't have any sensor noise into the picture, so I can't actually collect data from experiments and do
No, you
all
could
that.
collect data from experiments. So based on whatever sensor noise you have, you could provide that and you could get the model working. But if you have a little more of sensor noise and you give that as to the linear model, it won't work, or it will work very bad. So that's what I mean. It's quite
That would work
sensitive to measurement.
badly. No, that would work badly when I'm trying to figure out the states, or that would work badly even if I filtered and tried to figure out the states.
No, like I mean to say, just say you have the experimental data with you, which contains some amount of sensor noise, and you give that to do the regression for calculating A and B. And whatever A and B you get, you can get a good performance for that. But if you add a little more noise to it, just say a double of the noise that you have initially in your experimental data, and if you give that as your test data and see the prediction of the state that you get, it might perform very bad because it hasn't looked at that data. So you can see that it's quite sensitive to noise.
Oh, okay. Doesn't that
So
kind of defeat the purpose?
yeah, it defeats the purpose. But just say if you run a particular experiment, you would have a particular fixed signal to noise ratio of noise, right? You won't have variable different signal to noise ratio for different cases. So signal to noise ratio is fixed. Whenever you test it for new data, if the signal to noise ratio is fixed for that case as well, it's same as that for the regression or training purpose, your purpose would be met. But if you use a different signal to noise ratio to perform course.
Okay, so which means that it can do as well as the noise it has seen before, no better than
Yes.
that.
Yeah, no better than that.
Okay.
So that's one of the benefits. It cannot handle uncertainty and it should be fully observable. So these are the four conditions you need to have.
Manoranjan, you want to ask a question?
Yeah, I thought better noise resistance means it will be a good one. But I mean, I just wanted to know what are the advantages of this Koopman operator. Because I see that it's noise, I mean, it's very sensitive to noise, but what are the advantages of this?
Yeah, the main advantage is what I've known till now and what I've read in research papers is that the only main advantage is useful for designing controllers, and that's the major reason why people try to use Koopman. And there are other things. It depends on your field as to what your objective is. Like if we talk about our objective in ocean engineering, our objective would be so that we could design linear controllers.
Okay.
Ashwin, any questions? This looks very similar to, or at least like some sort of an inverse to what you tried to do, right? With system identification.
Yes, I get the regression part. It looks similar, but I'm not sure how it works for the controller. I've not made a controller model.
So I guess what he's saying is that you can now, if you have the system with the new states defined, you can apply linear controllers instead of going for nonlinear controllers and utilize the advantage of having the linear controllers for the system.
Yes, so from what I understand, like you bump up the order of that lift, it will come close to being non-linear. You're finding the system, right?
Yes.
Yeah, but we have to put a limit on that, right, to decide accuracy, a trade-off for accuracy and this, right?
Yes. So what happens is, just say if you are assuming daily basis functions, okay, and your actual dimensions of the states is 6 only in this case. So you assume n lift as say 100. That means you're assuming the remaining 94 states as your daily basis function, and you get some
Yes.
performance or say modeling increase. If you keep on increasing from 100 till 150, if you're not getting improved performance, you could probably stop at 100.
Yes, and you're running this regression over. Like here in this lift, you have one step, right?
Yes, and that is
And
one of the
those
other
and
demerits of Koopman. The reason
yeah,
why Koopman doesn't improve is because you're just minimizing a one-step prediction into the future. But so even if there is a slight error in one-step prediction, error will keep on increasing as you predict it for a higher number of time steps.
yes,
So that
and
is one of the
this
limitations of this.
and this minimization, A/B minimization, both the A/B minimization and the C minimization will be very computationally expensive, right?
Yeah, but I don't think if you stop it at say 100 only and lift its dimension to be 100, I don't think it's going to be expensive. It's manageable.
Okay.
So, okay. Following up on his point that suppose if I want to do the Koopman for which is looking 5 time steps ahead, let's say. So instead of the X and Y matrices having 1 time step staggered data, if I give it further more staggered data, does that do anything? Does it make it any better?
Right. Get your question. Could you please repeat?
So here Y is 1 time step away from X, right?
Yes.
So suppose I moved it by more time steps away.
Okay.
Would that change anything I won't be able to get the intermediate time steps, of course, I understand that.
Yes.
But can it capture the overall dynamics any better?
Yeah, you have to
So,
play with it. So I'm not sure about that. So lower
That
time
would
step that you
like,
give, you would get the model as, right?
yeah, that would depend upon the sensitivity of your system. So if your system is very sensitive, you will need shorter
Yeah,
time
we need
step.
a small time step. So it depends on the
You
dynamic.
have
okay,
But
all right.
like if you take a high number of time step and you minimize that, it's going to perform poor than what if it would have been if you would have taken lower of time. So
Okay.
because you're minimizing at each and every time instance. So if you observe Y lift is a whole matrix with k times. We are just not measuring one particular instance.
Correct. You're minimizing it over the entire domain, over the entire domain for 1 time step.
Yes.
yeah, this is like an overfitting problem. Underfit or overfit your system.
No, I don't
Will
think it's an
depend how many.
overfitting problem here because we're just minimizing one time step into the future. We're not minimizing it for multiple times.
Yeah, yeah. So like minimum you can go is 1 time step into the future, and maximum you can go is you can decide later.
Yes. So just say even if there is an error which is a little higher for one test print prediction, the error will keep on increasing as you proceed further. So that's the problem. So because the reason why it propagates is because in that initial condition, you know the actual state of the ship and extend it using the nonlinear functions that you have assumed. So you know the entire state. Once you know that entire state, it should propagate automatically with time. Just say find x at 1. Sorry, just say the lifted state is z. So you find z1. So whatever z of 1 that you get, you should use that z of 1 to predict what would be z of 2. And you should use the same z of 2 to predict what would be z of 3. Like that. So after that, after the initial conditions, not telling the model that it should be some nonlinear function of the first two states. It would depend on what A and B is. Like
Yeah, so
A
I
and
already
B
saw
says.
the initial state.
Yes, we know the initial states, which we can write it as the actual states followed by
Yeah, and
some
the
nonlinear
operator
function of the
will
state.
somehow map that initial state get like map the initial state onto the future state, right?
Like, what do you mean by future state?
Like initial state, you want xt, and you want to apply that operator to get xt plus 1, right?
Yes, right.
And you do that iteratively to get all
Yeah.
the.
So whatever x t plus 1 that you get, that won't be the exact states that I had assumed for the system. So I had assumed the first two states to be states followed by radial basis functions, right? But that won't be the case at x of 1, because you're using the A and B matrix to calculate x of 1. You're not defining it. So initially I defined it like first states are this and my remaining states are this. I defined it, and from there I'm propagating every time. So the error will keep on increasing.
So
if
like
there is a
initially,
decent error.
like initially, what do you have? You only have this one state or two states.
Yeah, whatever be the actual states of the system, non-linear system, you have that and the remaining states, which we can compute using our.
No, I think Ashwin, what he's saying is, suppose we start at some, after the training is done, let's say you gave it zigzag maneuver, turning circle maneuver, and a couple of other maneuvers to train it on the data. Now you have a model on hand where you have calculated this so-called A and B. And now I give it a new path or new control that I'm providing to the system, and I want to find out what the new trajectory looks like. Then his point is that because at every time step there is an error between what the exact system does versus the extended DMD system does, and that error will magnify over time as you apply it multiple times over and over and over again. So eventually you will see that the final at a large time step, you will see that difference between what the original system's response should have been would diverge from what the response your Koopman operator is giving. That is why the sensitivity to the noise. That is how I understand it. Because this operator is being applied at every time step over and over and over. Am I right, Shrenik?
So
Yes, right.
So this A and B matrix is fixed once you calculate it. And
Yes,
if
it's
it
fixed.
diverges from your
Yes, it's fixed. But you
not
could
exactly to your training data, even if you give it different maneuvers, it will diverge from your
yes.
actual dynamics.
One approach to solve that issue is you could probably change A and B at every fixed interval. So just say at every 10 seconds you change the A matrix, okay, A and B matrix, and then you get a trajectory which is close to that, and then again you change the A and B matrix at every 10 seconds. By doing that, what you're doing is you're kind of updating your model. So just say you started from 0,0, okay, with the actual states also being at 0,0, and you reach at say t equal 10 seconds, you reach at 1,1 for the Koopman case, for the Koopman model, and the actual ship state at t equal 10 seconds is 1,2. So there's a deviation
How
of
is
1.
that practical? It's not practical, right?
Yeah, it can be practical.
B and C all the time.
Yeah, we can do that, right? So just say at every 10 seconds, you keep on changing A and B, you can do that. So just say what happens is you kind of train the model, like you do the regression for just at t is equal to 0, you get an A and B. You simulate that for just at 10 seconds, and at 10 seconds, you will see that there is a deviation with the actual state of a ship, right? Okay. So now what you do is whatever state you get from the Koopman, or say from the Koopman model, you equate that to the actual state of the ship at t is equal to 10 seconds, and then again propagate it for 10 seconds. So by doing that, what you're doing is you're going till 10 seconds, you have a deviation, and then you're correcting the state to the actual state of the ship, or the actual state of the ship, and then again you propagate, and then you're correcting, again you're propagating. But for that to happen, you need to assume that you know the actual state of the ship. That means you need to know your state must be observable, right?
No, if I know the actual state of the ship, I need not do all of this, no?
Yeah, but we need to know the actual state only for one particular instant is what I feel. So just say I need to know at every just 10 seconds for model 2.
No, see, the main idea, or at least my understanding is this, that suppose I want to really see this method succeed, I have collected some data off of the craft by, let us say I have a ASV. I have run it over and I collected some data. From that data, I train the Koopman to get a linear system on which I can apply a linear controller. Now, if I want to update the system every 10 seconds in real time, it's going to be pretty difficult.
Yes, from controller perspective, you could probably keep A, B fixed. So it depends on your objective. In this case and our case, like it shouldn't be the case. You should keep A and B fixed. If that's the case.
Correct. So if I keep A and B fixed, then I have the real advantage of being able to use the linear controller or doing a essentially non-linear model being controlled by a linear controller of sorts.
Yes.
And as long as I do not have significant deviations, and the model has seen some amount of deviations in the data, it should be able to handle well and be able to track the trajectories. But then I'm only curious. I can only speculate. What is the downside? Where is it going to fail?
So for the first primary like challenge is selecting the observables. If you're not choosing right observable, you will not get good performance for how much of data you get. So that is one of the parameters. That is the downside of Koopman. So that's a major downside. And the other things that I told you, measurement uncertainty, observability.
Okay.
And finding these observables is not that simple. So you have to just do trial and error. If you are not interested in doing trial and error, you could probably use deep Koopman.
Yeah, my objective would probably be to use deep Koopman rather than trying to find them myself.
Yeah. So there is a paper by like Professor Umesh Vaidya's group, so they are the only one who have worked on deep Koopman with control. So you could probably see a lot of papers in the literature which has worked on deep Koopman, but that is for an autonomous system. That means that there is no input in it.
For non-autonomous systems, we don't have much.
For non-autonomous system, there is just one paper which I have looked at throughout the literature. So just a second, share the screen. So there is this paper, deep learning of Koopman representation for control. So in this paper, what they did is they tried to use the same approach that I had showed in the slide. So this is the code for deep Koopman. And what they did is they took a simple pendulum case, simple pendulum dynamics, and they compared this deep Koopman's results with reinforcement learning based. So use DDPG algorithm. So they compare that with this deep Koopman. But unfortunately, they haven't uploaded code for this. So I'm actually working on writing the code myself, deep Koopman, and I've kind of completed it. So if your group is interested in working on it, I could probably share that code and you can also try applying it on chips.
Okay, sounds good. If anybody is interested, we'll try to figure out and then we'll contact you. They will get in touch with you, and then absolutely we can start looking at something forward. I think
Yes.
Ashwin or Anand might be the right people who would be looking at something related to this area because they're looking at control for the ASV, and I think that is where the power really lies.
Yes, and with regards to its application on Ocean Engine, I don't think there has been anyone who has touched Koopman operator in Ocean Engine fields till now. So recently, only on May 2021, there is a group that published a paper with applying Koopman on ship. So this is the only paper that is done. But the demerit of this paper is that they haven't incorporated inputs in it. So they have just used dynamic mode decomposition with no inputs. So if you look through this paper, they haven't assumed any inputs. So probably there could be a good research paper on like data modeling of ships using extended dynamic mode decomposition with control. So
I think this group mainly works with Frederickson mainly works with CFD and that. So I don't think he's looking at the maneuvering stuff, is he?
I'm not sure. I haven't read the whole paper.
Yeah, it says maneuvering, short-term estimates. forecast trajectories, motions of ships, forces of ships operating in waves, offering a complementary efficient method to equations-based system identification approaches. That is where I was saying Ashwin's work is somewhat related to this. All right, sounds good. At least I have learned something. Thank you. Any other queries before we close this off?
Could you share some basic Koopman operator reading material, 101 kind of thing?
Yeah, sure. So I could share it now itself. I'll share a drive link. Maybe you could go through that.
Maybe Aditya, you can reshare that link on the WhatsApp group later on if anybody else wants to access it.
Yes.
Yeah, I've shared the drive link. Maybe you could go through that.
Any other questions?
And I've also added a README section over there. So maybe that has been like written in the order of importance, which are important papers as per priority. So you could probably start with that. That would be helpful in that drive link itself.
Okay.
And it's not just these three methods that I have presented in the meeting that can be applied. There are a lot of other approaches as well. So a lot of research has been done to handle uncertainty with Koopman with noise. Everything has been done. So to publish something new in terms of Koopman is very tough. But to apply it to a particular field where it hasn't been applied yet is something which can be done. So
okay, there you guys have it. Any other queries? Somebody else has any questions?
I have one question.
yeah,
Shrenik,
yeah, I'm on.
in the maneuvering equations of motion, we are considering the hydrodynamic forces acting on the hull. The term you are considering the non-linear model, like a Koopman model. So here, if you are applying the Koopman operator here, then it becomes a linear model. So it will create any kind of error in the calculation of hydrodynamic derivative on the force calculations.
No, I guess while defining the nonlinear dynamics, you're keeping the hydrodynamic derivatives to be fixed, right? So we're not changing the hydrodynamic derivatives.
Okay.
Right?
This is not a prediction of hydrodynamic derivatives, Krishnavelu. The derivatives are known or presumed to be known at least.
Yeah, just change the state of non-linear to linear model only.
Yes, in order to be able to use linear control methods on it.
Instead of the non-linear one.
Correct, because nonlinear control is much more difficult. You can use a array of methods which are available for linear systems, can then be applicable to the nonlinear system that you have.
Got it. Thank you, Shrenik.
Yep. Thanks.
If not, could I see everyone? All right, so Shrenik has given us a wonderful introduction at least to Koopman operators, and definitely he is interested in taking this forward. And anybody in the guild who is interested in learning more about it, I think he has given you now some material as well to look at, and also he'll be willing to have a discussion with you and to discuss what's going on and take this forward. So feel free to reach out to him and then let me know if anybody is interested, and we can connect you to Shrenik and take it forward. Okay. Yes, no?
Thank you once again for all your time.
Okay, thank you, Shrenik. So I'm going to stop recording here.